7.3 is really going to feel like more practice on that z-score idea. I first just want to describe a little more what that standard normal distribution does for us. It basically takes any normal distribution, no matter what the mean or what the standard deviation are, and it translates it to fit the standard normal distribution for which all of those values are calculated on our table. Now we know that 34% of the area is in this little chunk. Well, on the standard normal, 34% is also in this little chunk. You can see that this one is much taller to make up for the fact that its width is smaller. And this one is 5 wide, so it doesn't need to go quite as tall. But the moral of the story is that each of these areas is equal to each of these areas. And remember that the areas translate into probabilities. I thought it would be interesting to look at the Supreme Court justices and how long they're usually on the court. My research tells me that the average number of years is 16.7 years with a standard deviation of 9.8. That seems a little big, right? There's a lot of variation in how long people are justices. But assuming that that time is normally distributed, let's try finding the probability that a new justice serves for less than a year. So I'm looking for the probability that they serve for less than 1 year. We could use our normal CDF button, or we can translate that into a z-score, remember. And the z-score is calculated again by taking that x value minus mu and dividing by the standard deviation. That negative 1.60 then tells us how many standard deviations below average a 1 year term represents. Since I've converted that to a z-score from the standard normal curve, I can use the table to give me that probability. And it's set up really nice and easy because the less than is what the table is based on. If you need help using that table, just let me know, but my table is showing a probability of 0.0548. which suggests there's about a 5% chance that a new justice would serve for less than a year. How would that change if we were calculating a more than? The probability that a justice serves more than 20 years. Well, remember that the table doesn't help us with greater than, so we would have to use the complement. So we're going to take that and do 1 minus the probability of being less than 20 years. And while I'm at it, I'm going to convert that to a z-score. So I would take 20 years minus the mean divided by the standard deviation. And since 20 years is above average, I was expecting to get a positive z-score. 20 years is 0.34 standard deviations above average. So I've converted that x equals 20 into a z equals 0.34. And like I said, we can't use the table to do greater than, so I've also put it in complement form. We'll do 1 minus the less than version. On the table, positive 0.34 has a reading of 0.6331. But that would be the probability of serving less than 20 years, so we take the complement and we get 0.3669, so there's about a 37% chance that your brand new justice will be serving for more than 20 years. Now remember, there is a way to use the standard normal table to do a between problem. The basic idea is that you would find the probability of serving for less than 30 years and then subtract the probability of serving for less than 20 years. And that would leave just the segment between 20 and 30. We'd have to switch those over to z-scores in order to use the table. The z-score for 30 years is 1.36. That's with a bit of rounding. And then remember, for 20 years, we used 0.34. And now I can look those up on the table because those are standard normal curve values. The z tells me that. There's actually a big fold-out section in the front of your book that has all of these values on it, which might be easier to find than the back of the book version. And that came out to 0.28, a 28% chance that a new justice would serve between 20 and 30 years. And here I have that typed in the normal CDF function of the calculator. Remember, the entries in parentheses are low, then high, so that's where the 20 and 30 come in handy, and then your mean and your standard deviation. I think all of this is kind of a lot of work for one of those in-between ones, so I might default to the calculator for that type of problem too. Do you think that these numbers seem realistic? Because all of these numbers are going on the assumption that Supreme Court terms are normally distributed. Do you think that's true? Do you think they follow a normal curve? That would be an important question to ask if we're going to try to use the normal curve to calculate probabilities. So there's some criteria you should run through to see if you should be using a normal distribution. And honestly, even if your data meets all of these criteria, a normal distribution is normally an estimate of the probability anyway, because it would be hard to find data that is perfectly normally distributed. Criterion number 1, if you made a histogram of all of your data values, you would want it to look roughly bell-shaped, right? It should be mound-shaped symmetric almost. So definitely if it looked like this one, if it was skewed right, I would say that would not be appropriate for using a normal distribution to estimate anything about that data. This one is slightly better, but I still think that it might be a little iffy, so I probably would not use a normal distribution on that data. But over here, the results of this test, that looks like it's basically mound-shaped symmetric. So that would be safe enough to use a normal distribution to approximate those probabilities. Criteria number 2, you want to look at the outliers, because if you have too many outliers, remember on a normal curve, your outliers should be very low probability. So if you have a lot of outliers, the normal distribution isn't going to fit very well. And there's actually a calculation you would do. Do you remember what an IQR is? An interquartile range is the width between quartile 1 and quartile 3. Well, if you take that value times 1.5, makes it a little longer, right? And then measure that amount above quartile 3 and that same amount below quartile 1, you should not have too many outliers outside of that range. In fact, it says not even more than one outlier outside of that range. Criterion number 3, the skewness index, sort of a more scientific way to see if you have a bell-shaped histogram. And this one is looking bell-shaped, isn't it? I'm seeing the mean is 1.4, the median is 2, and the standard deviation is 1.5. Well, this formula calculates capital I, and they call that the skewness index. Is there too much of a skew on this? So we're going to take 3 times the mean minus the median, because I suppose the mean and the median should be pretty close if it's truly bell-shaped, divided by the standard deviation. And that comes out to negative 1.2. Now, in order to use a normal distribution, we were supposed to have a skewness index that was between 1 and negative 1. So that one was just barely too skewed to be called approximately normal. Do you suppose that comes from this side? It does seem like it's skewed just a little bit to the right. I really like criteria 2 and 3 because it's like a nice mathematical calculation, where number 1 and number 4 are a little more subjective. The fourth criterion is the normal probability plot. The normal probability plot is calculated using percentiles. It's a thing that your computer will do. So you put in your data, you run it through, it compares your data to where the quartiles should lie, and if you have a normal probability plot looking like this, that certainly doesn't look like a straight line, true? So if your normal probability plot looks like that, we would say, nope, we should not be using a normal distribution on this data. Where if your normal probability plot looks like this, that's pretty nice and linear. So that is a sign that I might want to use a normal distribution to analyze that data. So we were wondering, should we have been assuming for the Supreme Court justices that those were approximately normally distributed? Well, I took all that data, I made a histogram. Would you call that histogram roughly bell-shaped? I don't think I would. Let's try this outliers calculation. Not more than one outlier outside of 1.5 IQRs of Q1 and Q3. I have that data down below. And we could either do it in days or years, it doesn't matter. My histogram was definitely in days because those are some big X values. So quartile 1 is right here and quartile 3 is right here. So first let me calculate the interquartile range. Now we take that times 1.5, and we're going to check to see if there are any outliers beyond that much below quartile 1 or beyond that much above quartile 3. First quartile 1, then quartile 3. So that first one comes out to negative 6,131. And I don't have any justices that are serving less than that, so we're okay on quartile 1. For above quartile 3, I'm looking at 17,724 days. Do I have anybody that's served longer than that? I'm allowed no more than 1. And it looks like William O. Douglas served over 13,000 days in the Supreme Court. He was the highest. So there are actually no outliers that are beyond 1.5 IQRs of quartile 1 and quartile 3. What that tells me is that criteria 2 is a yes, meaning that those outliers don't disqualify us from using a normal curve. The next calculation, the skewness index, I'm going to need a mean and a median and a standard deviation. And my skewness index comes out to about 0.39. And that's within the allowed bounds. The skewness index just needs to be between 1 and negative 1, so there's not too much skewing on this data. So that means that yes, still a normal curve would be appropriate if you're just looking at the skewness. And then the normal probability plot, I found an online calculator for that. I entered the data, and the normal QQ plot looks like this. I think QQ stands for quartile or something. What I'm seeing is that towards the center, we're having a nice linear relationship. But then outside of the center, it's sort of looking more of like a logistic curve or something. Definitely curvy, right? We really don't want that curve in there. So I think I'm going to go with a no on the normal probability plot because those little end pieces just seem to be curving too much to be able to call that linear. So overall, if we look at all 4 tests, we had 2 that didn't disqualify the data, but we had 2 big no-nos. So I would say probably we shouldn't have been using a normal distribution to analyze that data, which means that these probabilities shouldn't be expected to be very reliable. Now, there are definitely plenty of situations where a normal distribution would work. We know that somebody's IQ, your IQ rating, is based on normal distribution. And birth weights of full-term babies, those tend to be normally distributed as well. There's a lot of naturally occurring normal distribution data sets to make this a useful topic to study.